urban neighborhood during a heat wave using coupled computational fluid dynamics simulations.
Thank you. Good afternoon, everyone. So the trees are living beings, and also they show a large amount of variation. This variation is also appears in their impacts. So we know that their cooling mainly shows in terms of shading and also transpiration. And then all these impacts are also dependent on the environmental factors. Then also the wind sheltering and reduction in ventilation is one of the possible impacts of these trees in urban trees. You see here a case study. There are mainly the urban trees that are present in these neighborhoods and are in the west of city of Zurich. You see there are two main streets in this cross section, and then this north-south oriented street have barely any trees, but west-east oriented street has many compared to that, and this has also an impact on the ventilation. We did a parametric study here, changing the leaf area density of the trees during a heat wave duration of 3 days in Zurich, and then eventually compared transpiration and then eventual impact on the pedestrian thermal comfort. Here you see the resolved buildings in the microscale and the location of trees. This is part of the neighborhood, roughly 600 by 600 meters. There we have the numerical mesh for the air domain, where we solve the airflow, heat and moisture transport, and then also to take into account the dynamic storage of heat. We have also additional subdomains for the facades. Here you see the active part of the facade for the roofs and also for the ground for pavement. Then we have the boundary conditions obtained from a mesoscale simulation, which is calculated prior to this microscale simulation. And here you see the extent of it, with the domain where the microscale domain is. These sketches show just the dimensions of these solid domains where we solve the dynamic heat transport. Then we have also the steady rain observation stops calculated for the wind flow, and these are calculated consecutively. So, for example, for a 3-day duration, we have every 20 minutes separate steady runs calculations where we update boundary conditions. And these boundary conditions for surface temperatures, it comes from this dynamic unsteady hem. It's heat and moisture coupled simulations. Here we ignore moisture from the surfaces, so impermeable surfaces, so it's pure heat storage. But in terms of wet surfaces and evaporative cooling, then we can also activate this and solve the couple. This is then coupled such that the surface fluxes, the heat fluxes are given from air, from CFT to solid part, and then surface temperatures are fed back to the CFT part at each time step. Then we have the vegetation, where we have volumetric vegetation models with different leaf area densities, and mainly for the transpiration we have stomatal resistance, which the tree regulates itself depending on the species of the tree. Then we have solar radiation, vapor pressure deficit, and the soil moisture content. All these depending on different factors, which increase depending on the environmental factors, the stomatal resistance. If the stomatal resistance increases, then the transpiration rate decreases. What we have as simplification here, we don't resolve the water potential or soil moisture availability, but I will show a sensitivity analysis towards the end and how it influences transpiration rate and leaf temperatures. Here you see finally the mesoscale, how we impose the mesoscale values. Here you see the wind speed at the lateral boundaries. We also do the same for temperatures. We impose in this blending layer source and symptoms for momentum and heat. And then these are the snapshots of these at mesoscale. You see the resolution of the mesoscale simulations, and then the result simulation at the microscale. And here, this is a 3-day duration. The temperatures increase during this period. The wind speed is higher generally during the daytime, and then the wind direction is mostly from west. and then you see without trees at pedestrian height, and with trees. With trees, you see clearly lower wind speeds at pedestrian height, but sometimes, depending on the wind direction, there are channeling effects. If I take one specific snapshot, when the wind is from west, you see trees clearly block this pathway during that time. For the air temperature, you see the absolute air temperature and how much the trees decrease or increase. So you see the impact, and then this rest with the same time step, you can see around these groups of trees, you can see lower temperatures clearly. Sometimes, if there is a connected pathway, this penetrates further into the city and the neighborhood, but there are also some locations where, due to the differences in ventilation, an increase in temperature. If I take an average of these volumetric trees, each of these dots represent a specific individual tree and averaged, and then you can see here the rate of transpiration, leaf temperatures with different size of trees. And you can see the LAD, leaf area density, have an impact on transpiration. We compared these with the available measurements in the literature, Konarska et al. In Sweden. We tried to select a similar temperature of air temperature and daytime. And then these are actually the measurement results, transpiration results that they had for LAD equals 1. So we slightly overestimate, probably because we don't here take into account the soil moisture availability. We assume ideal conditions in terms of soil moisture availability. But at different time of the day, you can see these values change a lot, depending on the day of time and also air temperature. What happens in terms of leaf temperature versus air temperature? There's always this trend that we observe, no matter what the size of the trees and also no matter what the time of the day is. What is happening here is, first, if you compare the heat source, the main heat source, solar radiation and latent heat, as the solar radiation increases, transpiration increases, but there is a limit to that, depending on the tree size. Even at ideal moisture, soil moisture conditions, there is a limit that the stomatal resistance decreases. So as this minimum stomatal resistance is reached, then the transpiration rate cannot keep up with the solar radiation. So then we have an increase in leaf temperatures, and this transpiration doesn't work so beneficial anymore. It's mostly the smaller trees with the lower leaf density which are affected by this. And then if we take into consideration also the soil dryness, probably in these dry periods and heat waves that can happen, then it has a different impact. So as a summary here, if the solar radiation increases, then the stomatal resistance decreases, but there is a limit to this at certain. If I take then into account this additional soil moisture availability impact, we reduce the transpiration amount by increasing the stomatal resistance, but also totally stopped transpiration and checked how much the latent heat changes and then how much the leaf temperature will increase, as a result how much the local air temperature increases. So this is the air temperature is actually in the crown of the trees, still not at the pedestrian level. But then you can see as an average, then the tree actually starts to heat up the local air. There is still some shading effect at the pedestrian level, but this is because of the local sensible heat exchange between the leaf and the surrounding air. Then we check the surface temperatures, compare them with the Landsat, available Landsat surface temperatures at that time. So Landsat gives surface temperatures in resolution, spatial resolution of 30 meters, but actually the thermal infrared sensors have a resolution of 100 meters. So we took this spatial averaging and compared without leaves and with leaves at different leaf densities. And then the results with the leaf simulations with the trees actually had an agreeable in the agreeable range with the satellite measurements. There are some differences. Of course, there is some variability in materials, and then also orientation of roof surfaces, where we always had flat roofs in the numerical model. So there is some variation there, but eventually there was not huge differences in the domain. Then we take air temperatures, humidity, wind speed, and mean radiant temperature with the surface temperatures and solar radiation, and compare UTCI in this neighborhood. On the left side, you see without trees. So if you look closely and you know the results of each of these terms, then you will see some similarities with wind speed. But what we clearly see, it's actually the shading and the local surface temperatures that really dominates the UTCI values. Also in the trees, there are groups of the trees where the UTCI decreases, the thermal comfort increases, but again, you see it's mainly the shading of the trees that defines. In this day, in a large part of the day, when we have very strong heat stress, which can be reduced a little bit, the average temperature there is 36 degrees, which then the UTCI values are a little bit lower than that, but still relatively high. So as a summary, then we observe the cooling in around large group of trees, and these can be transported further depending on the wind direction and the orientation of buildings. Also, the ventilation potential decreases clearly with the trees. Pedestrian thermal comfort improves due to the trees by 3 to 4 degrees UTCI, mainly by shading. And then finally, with the transpiration rate and the heat balance of leaves, small trees are more susceptible to higher leaf temperatures in heat wave periods, and this is probably important for pedestrian comfort, but also for the trees. And then tree sizes also change the local heating, because local heating during hot dry periods. So, thank you for your attention.
Time for one or two questions. Yeah.
One question about the model. How do you consider water availability in the soil? Do you consider the trees can always evapotranspirate? There's always water?
Yes, in the numerical model, it was not resolved. We only took into account by increasing by a parameter